that can either have an input or output capacity up to 600 volts. Some of our units will be a nominal, well actually all of them are nominal 208 input, but if the customer wants a different input, different output, we can swap out transformers and they're all multi-tapped. The unit internally is a Y connection, but the customer can have input delta or output Y, depending on the configuration. Of course, in this case, it's an OEM. If they want a special unit, we can put special transformers in there, change the taps, see how they're all listed, 480 to 208 tappable. We just change the actual delta reference or the Y reference, and we can change the voltage coming in and out of the unit and not interfere with the 208 nominal voltage and current that's inside the unit. And most of our units are all done modularly, but you can see how they make modules of each component. You got your control circuitry, your actual L, your inductor, your filters, DC bus, and on these units they have the option of EMI filters, input and output. So inside there's an LC circuit inside there. And then of course you see all the fans, current CTs, contactors, pair of modules. Those are, we have these options, these are maintenance bypass cabinets. These are like big, large J boxes that the customer can buy, put in front of their unit. Instead of installing new electrical connections, new electrical boxes, they come in where they can actually select their input breakers and put in a maintenance bypass breakers. One for the input, one for the output. And if the customer or electrical person of the hospital, building, city official, he can actually come in, turn off, and put one of the breakers in maintenance bypass, turn on the breaker, wrap around the whole system, work on the unit, fix it, fire it back up, and then turn the breakers back on in a maintenance bypass operation. And all these cabinets are large cabinets where they can bring in, tie their cables, make their connections in front of and after the UPS. This is actually an OEM option. Here we have a G8000. This is one of the larger units. This one happens to be a 100 kVA. All the magnetics and large transformers are in the back. If you want, you can maybe walk around and see if it's they're large magnetics. In the back of the unit, you have your output transformer, input reactors. On these units, we don't have the EMI filters like they have over the small cans. They actually have to make, fine-tune, and associate the actual LC filters. So here's our L and our C. So each reactor is associated for either the first, third, fifth harmonic region associated with against the L filter. And on the output, we have a transformer that's also a step down, in this case step up transformer from 300 to 480. And on the output, the transformer also has a 6.5% impedance. So the transformer on the output is now our output L, and we have a C on the outside, on this outside there. Okay. So that is our L. So on the input, there's your L, C, output, L, C. So the transformer also has that inductance put into it, or built into it.
The input side is an LC.
Yeah, there's three of them actually. Each one is separately detuned for first, third, and fifth harmonic.
Band project kind of thing. So all just those are.
Yeah, so that not one works hard. They all share, the first, third, first, or fifth, or 500 or 300 hertz, whatever it is. They're all fine-tuned to take care of their own current. Because of course, when you start filtering that, you get current. So they're all tuned for a certain specific range. Okay? And then some control transformers we have their feedback, fan, exhaust, like most of our units. Intake is from the front. We have an opening on the bottom. It's like a pie chart is cut out. Heat rises naturally through all the magnetics. There's like, they call them spacers, or bones, everything inside the transformer for airflow to go through and be exhausted at the top. And then we have heat sensors, just in case a fan was to fail. There's a sensor there that determines the unit. Hey, I've had a fan failure. My internal ambient has reached above 65 degrees and creates a fault.
So functions are mandated by law or just like
you can have units without things like this. It's like some of our units over there, they're optional. Okay? We can go back around up to the front and take a little look at it. thing over here. Now this one isn't not a double conversion. This is a what they call rectified front end, kind of like a drive. Input on the bottom, input contactor. There's rectifiers right there on the left side next to the fuses. That's your rectification. Comes in, goes to the unit, powers up the bus. The inverter is in the top section there. Those 2, 4, 6 IGBTs on top. Driver boards in the middle. And then the PWM coming out the top is forced through the panel into the transformer. And then, of course, sinusoidal is when you add a LC circuit, then turns it into a sinusoidal waveform and produces a 480 volt output. So same kind of thing flows through, rectification, DC bus, inverter. And then we have our driver boards, control board, display, and all of our power supply boards.
Those ABB ones, what are those?
Contactors. Input contactor, bypass contactor, output contactor. Yep. And then, of course, fuses for input and output. And in the center there is your DC chopper. DC connections are on the bottom, DC chopper in the center. So that'd be where your battery cabinet hooks up.
Yep.
When it's in battery backup, battery chopper chops it up to the DC bus voltage. On these units, since it's a, say, rectified front end, so whatever your input is, times, square root of 2, 1.44, DC bus is 680. Nominal.
So where is the power supply, for the control power?
For the control power, the power supply is right there.
This one?
Yeah, input power comes in here for detection. Power supply board is here. Gets all your positive 5, your 15, your control. But then also the driver board makes its own for its IGBTs. So that way everything's isolated. So if you ever do have a failure, drives are the same way. The board produces its own positive, negative 15, which is your turn on and turn off for your switching devices. Minimum vendor usually is 12 to 13 volts, minimal. Usually 15 to 16 is pretty nice, but it produces its own. High voltage comes in, there's rectifiers on the front there, on the right before the cap, and there's your power supply right there. There's your flyback transformer for all your switching. Yep.
Why are those chips capsules?
These?
Yeah, this circuit pulse.
Just because it's a bare circuit board,
Yeah.
and it's become a module, and for protection against the environment, protection against everything else, they coat them.
You can spray some kind of.
You can,
Yeah.
but we tend not to do that. We go one step farther.
It's purchased from the manufacturer.
That way, yes.
So
But you can do protected coatings.
Yeah.
A lot of times they do it on drives or high humidity or high moisture environments. You can, they call it conformal coating.
Yes.
It's pretty much the board is in a clear coat, is what it is. Makes it a little hard if you ever have to replace the board or work on the board. You must then bust through or melt off that material. But no, they do that for drives or anything in a harsh environment. Most time UPSs, they stay in a controlled environment, which is normally anything under 40 degrees C. So 104 degrees Fahrenheit. Most of the time a UPS won't go out of an environment more than 70, 80 degrees because it's usually in a building inside, controlled environment somewhere. And then the customer will normally have an evacuation for the, in this case, several thousand BTUs, which is also at the top. The UPS, most UPSs in there are in even in the mid 90 degree efficiency range. That still means 5% losses of 180 days. So that's quite a few BTUs to get rid of.
Yeah.
So. Right. And then we got one, if you want to take a closer look at this one, you can. This is that 4200, just like those over there, but a finished one. One transformer in this case, isolation, bypass circuits, a dual input, same thing. Here's your L circuit here. Control, contactors, same thing, input, output, DC bus, DC chopper, DC cap. And then across here are all your IGBTs, input and output chopper. So this is a dual conversion unit. And back up to the snubbers on each IGBT. And with snubbers, the closer you can keep them, the more effective they are. Same thing with DC bus leads and wiring to and from the IGBTs. The longer, the more noise acceptable they are.
But they are still a little far away, right?
No, the IGBT, the DC side's here on this side.
Okay.
Yeah. This is AC side, DC side. So we try to keep that close. AC side, and then of course that also applies to the gate leads. The shorter the gate lead, less turn on and turn off noise you have. Switching noise. And if it does get noisy, a lot of times you'll have to add ferrites, or change the board, or change the gauge of wire, or shield it to take care of that. That's into your engineering design there. We'll figure that one out. Okay? And then we have here we have the test facility. Like I mentioned before, all of our units go out 100% load tested, every one of them, no exceptions. So most time they'll get run overnight, like full load. You see how this one here on the bottom, this one seems to be a battery unit. In that case, all those are in series on one side, series on the other, 2 strings in parallel. There's fuses in there protecting each actual section. Each has its own fuse. So in lieu of a transformer, batteries. And in this case, this unit will probably have a battery backup somewhere around 6 to 8 minutes. And that's also proportional then to the customer's load. Less load, more runtime. And then they can parallel battery cabin onto this if they choose. And it just has Lexan on it right now so they can actually get in there and touch it while it's running. They have little test holes all over the place. They stick the probes in.
Would the generator backup plug into this, or?
Well, you can on the input of the unit, not into the UPS itself. Normally, that's a lot of times why UPSs and flywheels are used. A lot of times, customers will buy battery cabinet or flywheels. What they're doing is they're giving their IT guys or their building maintenance supervisor, whoever, enough time to say, hey, we've had a power failure. Outside, everything's dark. We're still running. Which then gives the generator enough time to power up, synchronize, get the frequency right, switch online. Most of the time these days, generators will synchronize in less than 15 seconds. Spin up to speed, sync the frequency, and transfer online. Which then, once it comes online, UPS sees power came back, it transfers back online, takes the grid from the generator. Or we have customers that have the flywheel. You know, we have a flywheel, what size of flywheel to give the customer about 12 to 15 seconds of runtime. Because that's about all that flywheel is going to give you anyways. Same thing. 15 seconds.
So several minutes.
That's the new ones.
Oh.
Older ones, it can take some time. Depending on how good it is, how efficient it is. But these days, a lot of the specs, you'll see anywhere from 10 to 20 seconds.
Oh.
Yeah. And it also depends on if it's running, idle, what state it's in too. You know, that makes a big difference too. Or how well maintenance it is.
So right now most of
Yeah. Negative 10 lift. There's one of our big battery cabins right there. Yep. When it's online, it's charging batteries in a float condition. Here's one of the XPs, which is what the trays go in. See? Pull them in, pull them out, push them in, lock them out. And then there's also a dead front that will screw on here just to keep them in during shipment and to keep hands out that shouldn't be in there. We have the control board here, driver board here for the IGBTs, caps associated with your LC circuit, DC fusing, AC fusing, input, and in this case the contactors don't have to be as big, input and output relays.
How do you design the IGBT drive?
The driver board,
Yeah.
the actual board itself, against the whatever the IGBTs need as far as the current, turn on, turn off, the actual rating of the current, the power supply for the positive, negative 15, and then flyback transformer big enough to carry all that current. And you got your actual transistors, turn on, positive and negative there. But to actually design it takes quite a bit actually. We leave that up to our PCB guys. I've never actually designed one. Yeah, we have actually PCB guys here on site. That's all they do. Software, PCB. That's all they do, along with the mechanical and electrical engineers.
So you guys does not use the DSP, right? Just for this one, is this DSP?
Yeah, that's the actual processor, yeah. But no, I don't know what kind it is. That's one of our newer localized ones.
Might be an FPGA or a MS.
Yeah. I'm not sure.
So does the DC-DC conversion principle still work in this high voltage?
Well, this one's actually not too high. This one here, but in overall, in the overall conversion, yeah, it's the same. Which we have G8000. Some of them will run in the low 300s. I've got one larger 500 kVA that runs at 480. Same chopper, same scenario, same frequency. All it comes down to is the switching frequency, the time base, the boost that you want to convert up to, which is all software controlled. You tell it chop to 500 volts, it'll chop to 500 volts. But there is a point to where in the design of the board, the amount that can be drawn and the gain of the device There's only a certain limit you can go so far.
Yeah.
But then you must have then redesign the board and redesign the software to handle that change in gain or feedback control. You can actually change that. But most time on our units, the topology doesn't change. You may have to change the IGBT rating or the frequency in which it chops. In our case, it's only about 7 kilohertz, or change the voltage reference.
So for this one, you use MOSFET, right?
Yeah.
Because the switching is very small.
Yeah. On these, or they're really small. This is low current here. It's like 50, less than 50 amps.
But high frequency.
I think these were running somewhere around 12, 14
Oh, that's high.
on the bottom, some of the smaller units.
Yeah. So what's this used for?
This can be used for IT,
Oh,
server
I see.
rooms.
Okay, I see.
We have units in Target, Walmart. We've even had some server farms use them for their maintenance backup. But this is mostly what you'll see in small businesses on your desk. They range from 2.4 to 22 kVA, just a larger unit, a little bit wider. But these will be what you use, like I said, in your office buildings. Yeah, single phase. But then your three-phase systems will be more, well, hospital, yeah, medical. We have UPSs in casinos. Well, they need backup too, right?
Yeah,
Got to keep them
that's
cameras going. Got to keep watching everybody. Philips Medical, Toshiba Medical. We've got UPSs in government buildings. We have UPSs now in the New World Trade Center.
You what?
The New World Trade Center. We have UPSs in there.
Wow.
Yeah, we got some UPSs in there. So those are, like I said, up to 750 kVA. Those are ones that back up the whole building. We can go up to 4 UPSs parallel on some of the big stuff. So you figure 4 750 kVAs in parallel. So that's, figure 3,600 amps total power at 480 volts.
Depends on the load side.
Exactly. Yeah. Okay. I was hoping he was still standing over there. Because